So the next talk is by Dr. Josh Day on scalable data analysis with JuliaDB and OnlineStats. Welcome him.
All right, thank you very much. Yeah, so my name is Josh. So I just got my PhD in statistics from NC State last February, which is why I get to add doctor to my slides now. But I work with Shashi and a bunch of other people, yeah, thanks, over at Julia Computing. And so since Shashi already talked a bit about JuliaDB, this talk is going to be online stats heavy, but we'll kind of come full circle and see some examples of how it works at the end there. So online stats is essentially the PhD, or the code version of my research at NC State. So I research online algorithms, which has nothing to do with the internet, but it's single pass algorithms for statistics. So the motivation here is, so IBM released this infographic a couple years ago called the 4 V's of big data. So there's volume, velocity, streaming data, variety, different forms, and veracity, which is uncertainty of data. So essentially in a statistics education, we learn about the right half of this thing. Right, so we're used to like randomness and like missing data and stuff like that, but what statisticians aren't really good at or don't have tools for is volume and velocity. So I'll argue that online algorithms can kind of handle both, right? So for volume, it doesn't matter if my whole data set is all available at once because I can update my model or statistic with just one observation at a time, and then obviously that also works for velocity. So like I just said, online stats provides single pass algorithms for statistics models in data viz. And then the extra requirement I have is that algorithms use constant memory. So that way we're not running out of memory as we're kind of reading huge chunks of data. So the highlights of online stats. So we get online updating of all these things. There's also some primitive functions for putting together parallel computing stuff. And then also there's a customizable weighting scheme, which I'll discuss in a second, but it allows you to give new observations higher influence over the model. So if you're observing something over time, you want the recent observations probably to matter more than the stuff that you observed a couple of years ago. And then there's also an extendable interface. So if you want to add your own online stats, there's an online stats base package, which makes this stuff very easy to adapt to new problems. So for online updating, I overrode the fit function from StatsBase. And so stats are parameterized by the type of whatever a single observation is. So for a mean, that's a subtype of online stat number. And so that's saying when I give a mean a new chunk of data, it's going to go kind of searching through that to see where it finds a number. And so as soon as it hits a number, it's going to try to update that mean's value. If I give it a vector or a matrix or something like that, it's going to keep iterating through that until I find an actual number. So I'll just show a quick example here. So we can fit a mean with a number, and I can see there's my mean, and the value is 1. If I go ahead and try to give it something that it can't do, so you'll see an error like this. So it tries to iterate through the string because I gave it something that wasn't a number. The first thing in that iterator is a character, and it says the input for mean is a number, but I found a character, and I can't kind of drill down any further. So one of the benefits of this is that this works for any abstract arrays or tuples or name tuples. Basically anything you throw at it, it can kind of iterate through, and since it's Julia, you're going to get fast compiled code. Okay. So the primitives for parallel computing are through this merge function. So it's useful apart from parallel computing, which I'll talk about a little bit later. But essentially just how it works is that all these online stat types are just mutable structs. So you can kind of, we overload merge for all these things, so then you can join them together kind of after you fit them on 2 separate chunks of data. So if you have, 8 different workers, you can kind of copy your mean to all your 8 different workers, run it through your 8 chunks of data, and then merge them at the end. So it's just it's an embarrassingly parallel problem. So another thing in online stats is the ability to weight functions. So many updates can be written just like as a function of the value of the stat, whatever that thing is. Maybe some kind of sufficient statistics, which I'm abusing the term, but some kind of state that helps you compute the value. A new observation, we'll call that xi, and then n, the number of observations. So in general, your update you can kind of write as a function of those things. And so the online stat object, that's kind of storing the value, and it's storing the sufficient statistics, and it's storing n. So you're kind of storing the state, and then you get a new observation, and you can update the value and state and everything else. So here's what the online update looks for a mean. So we get this 1 minus 1 over n times whatever the previous value was, plus 1 over n times xi, which is our new observation. So if we just rewrite these weights as just a general function of n, or the number of observations, we can now apply like different kinds of weighting schemes to this. So OnlineStats has things like equal weights, so that on the previous page that was just 1 over n. We can do something like an exponentially weighted mean by giving an exponential weight. And then there's things that are mainly for stochastic approximation procedures that are also in OnlineStats, which I call learning rate, which is parameterized as 1 over n to the r, whatever argument you give it to it. So here's a plot of how all these things compare. And it's really only useful when you kind of compare how these things compare to equal weight, which is the kind of the more solid blue line that goes towards the bottom. So the question is here, like, why do we care? Like, why do we want to weight things differently? So you can also provide your own weight function, so you're not limited to just the types that OnlineStats provides. But the idea is shown here. So if we're observing some data over time, so this is something called like concept drift or parameter drift. And so it just means that the true underlying parameter is changing over time. So if I'm trying to compute like the mean of this data, like statistical consistency doesn't make sense because I don't have like independent identically distributed data. This thing is actually changing. So if I'm weighting my first observation as the same as my most recent observation, I end up estimating the wrong thing, right? So this blue line is the equally weighted mean, but I'm estimating the wrong thing because the data is actually changing. Whereas if I weight observations relatively higher with the exponentially weighted mean, I'm able to actually kind of keep up with how that data is changing over time. So this is a very trivial example, like it's just a mean, but the same kind of events can occur with more complicated models like regression and decision trees and everything else. Yeah. All right, so for extending OnlineStats, so the package is OnlineStats base. Basically, in order to do that, you just need to import the OnlineStat type underscore fit and underscore merge. And so here we're just going to make a counter, which is something easy for us to do. So we'll import that, and then we'll make a new mutable struct called counter. We'll make that a subtype of OnlineStat. And at least in this case, we're only going to count numbers. So we could put anything in there. If you want to count strings, you would have to make it a subtype of OnlineStat string. But we then store the n, the number of observations, and then we create our fit and merge methods. So fit on whatever new observation that is. So for a number, we're just going to increment the n by 1. And then when we're merging these things, we're just going to sum those two things together. So let's go ahead and do this. All right. So I've added those things, and now when I fit my counter on, I don't know, whoops. Some new observations, so we can now see that I've counted those things, and there's some kind of automatic methods that get involved for showing what OnlineStats look like, which is kind of helpful. Yeah. All right, so I've really only shown means so far, but OnlineStats can do a lot of other things. So the idea was that we kind of started with just kind of like the basic summary statistics that you do when you look at a data set. So you want to do means and variances. You might want to look at count maps, so that's the count of unique elements in your data set. Things like autocorrelation, histograms, quantiles, maximum and minimum. And then moved on to some more complicated things. So here are some more like statistical tools. So reservoir sampling is a way to take a data stream and then you're calculating a sample without replacement. And there's also an online version of the bootstrap in statistics, which is on OnlineStats. You can do things like linear regression. So one thing to note is that many things you can't do analytically, like it's impossible to do. So like means are really easy, but it's actually impossible to fit an exact logistic regression using a stream of data. So a lot of these things use stochastic approximation, and some of these are algorithms I worked on during my PhD. But for things like linear regression that actually has like a true sufficient statistic that can be updated online, linear regression is something that you can do exact, along with ridge regression and ElasticNet and Lasso. But for some of these other things, so for general models that are regularized but they're linear in the parameters, so that's stuff that we can do approximately through stochastic gradient descent and kind of other variants of that. Some newer things that I've added are a naive Bayes classifier, and then an online version of decision trees and random forests, and then we also have k-means clustering. So we also have group by operations, so I can give it 2 columns, so JuliaDB will kind of handle that group by stuff for you, but if you're kind of working outside of JuliaDB with OnlineStats, you can still do group by operations. And then hyperlog is an approximate count of unique elements, so if you're looking at a really huge data stream, it approximates the number of unique items in there. And then you can also do fitting of parametric distributions, like beta, Cauchy, gamma, log normal, and so on and so forth. All right, so kind of separate from the statistics and modeling stuff, so OnlineStats allows you to fit a bunch of basically objects that create like sufficient statistics for visualizations, essentially. So this thing on the top left is something I call partition, which I'll talk about in the next slide. But as a data stream is coming in, you kind of chunk up that data stream into different sections, and then you kind of plot whatever statistic you're kind of summarizing the data with. I guess I'll talk about what that means in a second. So the middle one on the top is called the mosaic plot, which is just a useful tool for comparing categorical distributions. The thing on the top right is what you get when you plot a naive Bayes classifier, so it kind of shows you the group probabilities. The bottom left is an approximate scatter plot, so the idea is that instead of plotting every single point, you kind of group them into bins, and then we have histograms there, and then we have, again, so kind of like an approximate scatter plot where sections of the data are summarized by histograms. But so one neat thing about this one on the bottom right is that so every point of your data set is guaranteed to be covered in one of these shaded areas. So I think I used a couple million observations for this. I don't actually have to plot a million points. I just have to plot kind of these summaries of the densities of the points underneath. All right, so I mentioned that partition objects. So this is something I worked on relatively recently, and I think it's pretty cool, so I'm going to describe how it works. But so for a partition type, you give it a statistic, so it's how you want to summarize your data with, and then you also give it a number. And that's like the number of sections you want to split your data into, and then you kind of summarize each section with whatever that statistic is. So here I'm saying, for my data stream, I want it split up into 6 pieces, and I want each piece to be summarized by the maximum and minimum. So here, say I've already fit whatever this is, 12, 20 observations or so. So I have 6 different bins, and so this blue dot represents this extrema object to the maximum and minimum. But now when I add a new object, so I've run out of bins to put the data into essentially. So I'm going to add a new bin, but then I'm going to merge those 2 together. So that's another usefulness of those merge operations within OnlineStats. So it's not parallel computing, but it allows us to kind of continually increment this for no matter how many observations that we have. So I run out of bins and I merge adjacent stats, and that way this object can kind of grow forever. So here's just a quick comparison of what this looks like. So this is only 10,000 observations, but when I split, so I think I split this up into 100 different parts. When I plot the extrema of 100 different parts, it looks like what it is on the right, whereas if I plot every value, it looks like what it is on the left. So the idea is that like your brain can only comprehend so many data points. So as I go up to millions of observations, those are things that get harder for my computer to render, and I don't actually really understand all that information because there's a million things there. So I'm essentially plotting like the sufficient statistics of what my brain can understand. Is kind of how I think about it. All right, so that is the gist of OnlineStats. So I think most of you were just in here for the JuliaDB talk, but I'll just kind of reiterate about what it is. So JuliaDB is it's both distributed and indexed, so sorted by multiple columns, and both of those are optional data tables. So it gives you really powerful syntax for like selecting, filtering, and mapping functions to data, and then it also gives you some out-of-core processing with OnlineStats. So with JuliaDB, I don't actually need my data set to fit in memory. And JuliaDB handles that part, and then for running statistics and models on it, OnlineStats handles that part. So from the highlights for JuliaDB, so going from small to big data sets is trivial. So I essentially use the same code for doing the same things. Even though, so JuliaDB is doing a bunch of different things underneath, like it's distributing the tables, and it's kind of doing this fit and merge operations for online stats. That's all kind of going on under the hood, and I'm not really worried about it. So the benefit here is that like you don't have any need to switch or like glue packages together. So in Python, I think people would use like pandas and Dask. When I search for like what do I do when I run out of space, well, the first thing was like, well, buy more RAM. But then the second one was like, oh, you should try sparklyr. But again, so there's extra costs like with your brain, right, of needing to learn new technologies in order to do the same thing that you've already done. It's just that your data is bigger. All right, so JuliaDB and OnlineStats work really well together. And that's just because JuliaDB puts together those parallel computing primitives that OnlineStats already has in there. So reduce, so similar to like MapReduce, and it's kind of a slight abuse of the term, but if I reduce a table with a mean and a selection, it's going to run that mean kind of over that selection. And same thing with group reduce. I can essentially do a group by, but I'm using an online stat instead of some arbitrary function. All right, so here is an example that I can actually run in front of everyone here. So here is so the stock data set. So I just stole it off of kaggle.com, and so there's over 7,000 CSVs, and it's about 700 megabytes total. So let's get out of this real quick. Okay. So I haven't loaded JuliaDB yet, so we'll load these things. All right, so we can see we have 7,195 different files here. So I'm going to load these files. I'm going to give them a file name column. So I'm going to add a column that says what file is it coming from. And then I'm also indexing by the date field, which I think didn't get shown there. But I set the index column to be date. So I can then call group reduce, and this thing goes through and fits it. So I haven't done anything distributed here. I haven't added procs or anything like that. So here is my, well, I'll just leave that here for now. So here is my kind of analysis with only looking at the first 5 files of this thing. So if I just want to expand this to a much bigger problem, so really all I have to do to change my code is I just need to add workers. So once I add processes, so JuliaDB is automatically going to load these files into a distributed table. So I'm going to set the output to be some directory where you want to save the data on disk, and then I'm going to say load this data in 100 chunks. So a chunk just means essentially like how Julia is going to handle the CSVs. So it's going to save 100 different chunks that load, well, so it's going to be the number of files divided by 100 CSVs into each chunk. All right, so let's, no. All right, so this will take an extra second just because I haven't loaded anything yet. Oops, and I lost my plot. That's okay, so I think we're in the clear for now. All right, so I've added 8 workers. That's the number of workers available on my machine. Loading JuliaDB online stats. Those are my 7,000 files again. And now as my table loads, so as this is loading, it's saving onto disk 100 different chunks of this file. So now when I calculate a mean or something like that, it's actually going to compute this out of core. Well, if it needs to. And since I just launched Julia, we're also timing some compilation time and things like that. Okay, there we go. So now notice that I've loaded this thing, and it now says distributed table. I have 15 million rows and 100 different chunks. And then when I go ahead and calculate this, there we go. So now I've calculated the average of each one of those 7,000 stocks. All right. So I put big in quotes just because this isn't actually making my computer run out of memory or anything like that. So for an actual big data example, so unfortunately, this takes probably too long for me to do in a talk. So I stole a year's worth of New York City taxi cab ride data. So it has things like the where and when they pick people up, and then how long the ride was and how many people were in the vehicle and stuff like that. So I have 12 CSVs, so it's all the data from 2017, and it's about 17 gigs on disk, about 110 million rows. Oops, and I didn't pull this up prior, unfortunately. All right, so this is a notebook that I saved earlier. But just to kind of show you how kind of easy it is to go from this like small data analysis to this big one, all it takes is a few small changes. The biggest one just being add procs. So here I only added 4, and that's because the CSV files I was working with was very big, and I didn't want to kind of crush my computer, so I was doing other things on it at the time. So I just added 4 processes. I said using JuliaDB and OnlineStats. I found the files I wanted to load, so here are all the CSVs I'm loading. I loaded these and indexed or added a file name call. So that took about 2.5 minutes to do. And then so here I restarted Julia just to show that I can now load this data set from the binary files that are saved. And we can see that reloading it only takes 0.3 seconds. So reloading things is almost immediate. So yeah, so in general with CSVs, you probably only want to load CSVs once because it's a very inefficient format. So with JuliaDB, you can load CSVs, save it as something that Julia can then kind of deserialize instantly. And then once I go ahead and calculate the group mean, or the group reduce on this one, so this took about 40 seconds. And this is truly running kind of out of core, just on my laptop. I don't need a cluster to kind of do this analysis. And again, this is like 17 gigs worth of data. All right. So if you want to know more and get started with this, so please, yeah, ask me questions or Shashi. We'd be very happy to talk about it. Yeah, so there is the link for the source and then the link for the docs. So I hope you find it as useful as I kind of had and enjoy working on it. So thank you.
Well, that was a great talk, Josh. Thank you very much. We have plenty of time for questions. So I'll bring the microphone around. We'll kind of work right to left.
Hi. That all looks great. I'm afraid I'm going to ask a question about JuliaDB rather than OnlineStats, but it was something that you brought up at the end about saving the data in chunks.
Yes.
It seems like periodically the underlying file format for doing that changes, and I can completely understand why that might be, but it can be slightly frustrating when we're moving files around. So, I mean, is it going to stabilize, or is it going to remain just something that we have to put up with carrying the CSV files around as well, just in case it changes again?
Yeah, I mean, so it's based off of like Julia's serializer, so that's right. So it changes between versions. So I don't know if Shashi has plans to make this like a stable format, or I'll let him answer that.
I think we want to make it use parsing, the format that very close to what we do, but like having formula.
So it'll be great once that uses Parquet permanently. So, if you
So thank you very much for your talk. Going to the plotting part, first of all, is this plotting provided from OnlineStats immediately, or there is like a OnlineStats plotting package? Or
So it uses plot recipes.
okay.
Recipes base is like the plots ecosystem, really lightweight package for creating recipes of how to plot arbitrary objects. So these are all kind of objects in OnlineStats, but then you can just go and plot them, and then it runs through the plotting backend.
So my question is a bit more on the scientific side. So you tried to argue how you think these are better somehow representations, but how would you cope with the fact that, first of all, these may not be actual unique representations? For example, especially with this kind of Weierstrass function that you showed. And also, how do you cope with the fact that if you want to use this in a scientific kind of publication, you have to also explain how you actually do all this kind of processing on your data to plot it and stuff like that?
What was the first part of that question again?
So that I assume that many of these kind of representations, because they are coarse graining, they are not a unique representation of your data. So a different data set would have the same plot.
Well, it's possible. Yeah.
Yes, it's possible.
Yeah. So the idea here for me is that this so it gives you a very coarse view of your data. So I guess that was a good word, choice of words there. So it does give you a view of your data. So if I have 100 million observations, with most data sets like that, there's no kind of plots, like plots.jl, you wouldn't be able to just plot those things automatically. But with OnlineStats, you could run them through in a couple seconds, and then you can at least get a coarse view of your data. It might not be the best view, but it's something that you can do. Yeah.
Two questions. One quick one. You mentioned you had a comment that it'll run out of core if it needs to. How do you decide whether you make the decision?
I did not write the scheduler. So that's Tom and Shashi could do that better.
Okay, I had a little question about the online mean. Is it sensitive to numerical error? Because when I do sums, then sometimes you need to do it.
Yeah, I mean So it's exact to floating point precision, but it actually is fairly stable the way it's implemented. So most things, so by forcing things to be like constant memory, so one part of that is. So another similar idea, I guess, is that like every kind of sufficient statistic is stored as a sum and not like a mean of things. So you're never going to like run out of larger than ints or anything like that, or larger than float 64s, because everything is stored as a kind of a mean. So basically, if you have IID data, those things are kind of converging to something.
Okay, thanks.
So regarding the streams, clarifying question. It seems like they're like streaming algorithms, but you're still taking all the data at once, whether it's in JuliaDB or from a file or from a static vector.
Yeah. So
do you have plans for actual streaming where you're receiving things from somewhere else, listening for them?
Yeah. So I'm leaving that to kind of other people to decide how to use. So I'll mention. So Jacob Quinn gave a little talk about Domo, and so he mentioned that they use kind of a custom version of OnlineStats that kind of calculates the summary statistics as they're reading in data. So I think you do need to do a little bit of customization in order to do it on truly streaming data. But this idea is that with JuliaDB is that so JuliaDB has one chunk of data, you run your stat through, then it loads the next chunk, but then you can run the stat through that chunk and then merge them all at the end.
This is more about JuliaDB. You had mentioned that it's sorted rows by some indexes, some primary key. So won't that make insertions and deletions costly if the database is large?
I guess the efficient way to do insertions and deletions is you get a big chunk of CSV file which you want to add to your table, and then basically merge it with the previous one. And deletion, you can do an anti-join to get a deleted thing. So you have to do those things in batches. In an analytical database, you assume that you're just working with a set of data.
Load once,
Load
analyze
once, yeah.
many.
So we want to optimize for that.
So we need Julia transactional DB. Okay. I think if it's very short.
Josh.
Yeah.
So you had at one point someone using OnlineStats base and implementing underscore fit and underscore merge. What do the real fit and merge methods add over top of that?
Yeah. So it's basically to make height wide enough for dispatch. So if I fit whatever, some online stat that I've made on some iterator, then I just kind of want that to work out of the box. Or if it's like an iterator of iterators that contains number, then when I fit a number on that, like, it'll still work. Yeah, and so that's and then so merge does a check on the inside to make sure that the number of observations isn't 0 for both stats or something like that. 'Cause that would be ill defined. So there's a few kind of just error checking things essentially with this.
Okay, great. Thank you. Let's thank the speaker again.